Kepler's third law's original formulation that the period square is proportional to the semi-major axis cubed of an orbit of a planet is incomplete. So this original formulation assumes that the period is measured in Earth's years and that the semi-major axis is in astronomical unit, and then the constant of proportionality is 1. Now, we derive in class Newton's version of Kepler's third law, where this constant is expanded on, and if the units are in standard units, so that the period is in second, the semi-major axis in meter, then the constant of proportionality becomes 2 pi squared over universal constant g and the mass of the sun, ms, in kilogram. Newton's version of the equation can be in fact applied to any system. Now, all you have to do is replace the mass of the sun with the mass of the central orbiting object. The central object would be the big mass, and then the orbiting object would be much smaller mass, therefore negligible. And here's a problem. What if the mass of the orbiting object is not negligible? Newton's argument is that both masses, m1 and m2, should be treated with equal footing, and of course the dimensions of the equation cannot change, so it would not make sense to multiply with the second mass. So instead we would have to add up the two masses. Now, if one mass is much larger than the other, then we revert back to the original equation, where big M would be the dominant mass, the central mass. And if the two masses are relevant, then they are both taken into account. And the kind of orbit we would observe here is that there is a common center of gravity, which is the fixed point, and the two masses would be in orbit around this barycenter or center of gravity. So Newton's final version of Kepler's third law is that the period square is equal to 2 pi squared over g times the sum of the two masses involved, and one of them can be ignored if it is much smaller, and then you multiply by the semi-major axis cubed. Now, the question is, can we still use Kepler's original formula? Can we still use this original system of units, which is very convenient? Well, here we're missing the mass. So, in years and AUs, we can express the masses in solar masses. In other words, in multiple of the mass of the sun. So you would have the period squared equal to 1, this constant is 1, except we would include the masses. 1 over m1 plus m2, multiplied by the semi-major axis cubed. This alternate system of units would use Earth years for the period, would use astronomical units for the distance, and solar masses, ms. So the sun has a mass of 1 solar mass. So in our solar system, a planet would have 0 mass compared to the sun. The sun would have a mass of 1, and you would be back to the original equation. However, you can also use it in a different solar system with a star of arbitrary mass different than the mass of the sun, and then either a second star sharing the orbit or another planet. This becomes a universal equation, and you would have access to easy to deal with, a more intuitive set of units. You could also use standard units. When do we use standard units rather than these more convenient solar masses and years unit? I would say whenever the mass cannot easily be expressed in solar masses. For example, a satellite orbiting the Earth, it would be a bit silly to express the mass of the Earth in solar masses, so I would rather use SI units in that context. However, in a binary star system where two stars orbit each other, both of them having a mass comparable to that of the sun, then using this system of units makes more sense. So use your judgment.